A few months ago, I went online shopping at AliExpress and eBay, and I bought a bunch of sensors and development boards for future projects. Hello, I am Mainello, and it's time for my first project. The project is about building a rover. I've got a project description at Instructables. The link is down in the video description. More about them later. Let's get started with building. At the beginning, I just took a wooden board, an Arduino Uno, a motor driver control shield, 4 DC motors and wheels attached to them, and a power bank. The classic starter kit for making a rover. I put everything together and gave it a test drive, and it worked. And just a few iterations later, I had this. I named it the Pioneer. And as you can see, it already works. I can start it remotely via my laptop, and it does drive. It already sends GPS data to my laptop. It just has some problems with steering. So I thought I'd be almost done, like 80% or so, but the life of the Pioneer proved to be a long and difficult one. The next iterations included getting a stepper motor and mounting it in front of the rover, adjusting the code, getting a new wheel, adjusting the mounting of the stepper twice, powering the 12-volt DC motors with 17 volts instead and changing it all back again, adjusting the code again, putting the GNSS sensor on a stick, exchanging the stick of the compass, try to calibrate the compass, changing the compass, actually calibrating the compass, adjusting the code again, gluing the wheels onto the motors because they just kept falling off, exchanging one of the motors because the gear was broken, and a few more iterations. But then, finally, the next version of the Pioneer was ready to go. And here you can see it move. Let's have a look at what the rover is actually supposed to do. So, it is supposed to drive the contours of the letter pi. For this, we will first have the rover back here, and then it will need to drive forward, turn for 90 degrees to the left, drive a little bit forward, drive backwards, and so on. So the heart of everything is the Arduino. It will get information from the buttons and sensors and control the motors and LEDs as well. The GNSS data that the Arduino received, it will then transmit via a USB cable to the BTT-Pi. BTT-Pi runs a Python code that reads the GNSS data that it gets via the USB cable, and then it hosts a server that I can look at my laptop because we are connected with the same Wi-Fi. And at this server, I can see the visualization of the GNSS data. So, in theory, the rover is supposed to drive this letter contours, and I can see at my laptop in real time how the GNSS data points are coming together to the letter pi. Now, most importantly, what is a BTT-Pi? You'll probably never have heard of it because it's quite unknown. It's not really common yet. It's basically a cheap version of the Raspberry Pi. It's a copy, and it imitates how the Raspberry Pi 3 works. And yeah, more about that one later. The Arduino has a wiring diagram that is also quite interesting. It's here. You got the GNSS sensor, the compass, two LEDs and a button. The red LED will be turned on first. The rover will not move until we press the button. As soon as we press the button, the green light will turn on and the rover will start moving and drive the letter pi as described before. Here we got a board which is controlling the two DC motors for the wheels in the back via pulse width modulation. This is the stepper motor which is located in front of the Pioneer, and it requires a stepper motor driver, which again is connected with the Arduino, but also with the 12-volt supply, which I showed here as a set of batteries. I used a power bank instead. And this is the BTT-Pi. As you can see, you got the USB cable for the data transportation, data communication of the Genesis data. And yeah, that's it. So let's have a look at how the theory that I just explained is translated into code. We're looking at the code that runs on the Arduino, and it starts with just some initialization, some definitions of variables, and then for the sensors that we are using, those are just standard definitions and referring to the pins that you can see at the wiring diagram. We then get another setup and starting a serial communication at a certain baud rate. This baud rate is important later on when we are looking at the Python code, because the Python code will use the same baud rate for the communication. The GPS is also talking via serial communication, and it has a certain standard baud rate, 9600, but it has nothing to do with the serial here. Just a few more definitions, and then the compass setup. The setup of the compass and anything else regarding the compass is in a different ino file. Setup is here, again, just a standard setup, and the reason for the compass stuff being in a different file is because I just copy pasted everything from other examples and other people's code, except of course for the error compensation that is doing the calibration of my compass. But you will have to do your own calibration, of course. And then we are already starting to get into the loop. First, we are in another loop which checks whether or not the button signal changes. And as soon as we do press the button, we are turning off the red LED, which has been turned on previously in definitions, and we are turning on the green LED, which has been turned off before. And then we are going into the movements that I just described before. So first moving forward for 20 seconds and turning left for 90 degrees, moving forward for 6 seconds, moving backward, and so on and so forth. As soon as all of those movements are done, we will stop all the motors, write high for the red LED, so turning the red LED back on. So then the red and the green LED will be turned on. And finally, we are entering an infinite loop where nothing happens. So let's have a look at the movement functions. Forward. First, we are defining a previous angle, which is the current heading of the rover. So this is the heading that we want to keep. So as soon as we are moving and deviating from this previous angle that we got, we want to steer a little bit and get the uh, get the rover back on track and more towards the previous angle here. All those lines here with the analog writes, they are for turning on the motors, the DC motors. First, we're setting a rather high value because they need just more power to start moving, and then reducing the power after half a second of initial boost so that the rover does not run away and is keeping it at a reasonable speed. Then we got heading diff. Heading diff is exactly calculating the difference between the previous angle that we had and the current angle that we get and that we constantly update, because here we got another loop, which we will only exit when the driving time, which is what we passed on to this function, is being exceeded. And this heading diff will then decide whether we're steering a bit left or right, depending on its value. And if it's lower than 0, turn left. If it has a positive value, we'll turn right for 1 degrees each. So it will control the front wheel and steer it left in this case for just 1 degree. And in order to prevent oversteering, we are setting a limit for 6 degrees in total. And also just updating at a certain rate. In this case, just every 0.1 seconds, and then adjusting the angle. Here, this time is being compared to a variable called I, which is being initialized up there. You will figure it out. And yeah, then at the end, when we are exiting the loop, which is happening here, we're checking which direction the front wheel has, because it might be still at 6 degrees to the left or to the right, and just turning it back, putting it straight, and then we are returning. So the first forward movement is done, and the next thing that we need to do is turning left. And let's have a look at that one too. Starts pretty similarly, just that we will start by turning the front wheel left 40 degrees and getting previous angle again. This time we want this angle to turn for 90 degrees. And this is exactly what's being checked in the loop that's coming up. So we got a heading difference again, and checking or like comparing this to the turn degrees, which is the variable that we are passing on to this function. And the way that it works is that the inner wheel is spinning slower than the outer wheel. So we got a steering here, and also we got the front wheel that has been turned. And we're not turning them on constantly, but just for 0.25 seconds. And then we stop. Stop the motors and we wait for 4 seconds because the compass will need a bit of time to get the new heading. And only then, when everything is settled and quiet, we get the new angle. We're comparing this to the previous angle. We are calculating a heading difference and so on, like comparing this to the turn degrees, as I told you. At the end, we're turning the front wheel back to the right, so that it's straight again, and the next movement can begin. And going forward, turning left and moving backwards are pretty much the only movements that we do. Moving backward is the same as moving forward, just backwards. And yeah, in the end, in the very end, to write the curve on the end of the right leg of the letter pi, we got a third function, which is called left curve, but it's very similar to the ones that I described before. One more thing that we can talk about is the GPS read-write. We're calling this all the time, as often as we can, because this function will get information from the GPS sensor and it will write this very information on the serial outputs, on the serial port that we open, not on the port, yeah, just the serial communication thingy that is being read via the Python script, which runs on the big BTT-Pi. So let's watch the Pioneer perform. Press the button and it's going straight. Then it's turning left with small impulses to the left. The front wheel is resetting. Exactly. It's going straight, then moving backwards, constantly correcting its course, then moving straight again. The second left curve, then resetting the wheel one last time straight, and then the last bigger curve to the left, which is and here you can see how it's correcting its course so that it's always parallel to the white line. And meanwhile, I am receiving GNSS data, which is constantly updated. Let's have a look at the Python code that makes this possible. Now, this map that we've just seen has been created via Python, the Python code that I mentioned already a couple of times. Now, let's have a look at how this works. The code just starts with some imports of libraries, like modules that we are going to need later on. And here the actual code starts, and this definition of Arduino is already the first interesting line. So we are initializing a serial communication at the COM port 5. At least this is the port that I am using. It might be a different one in your case. It might be COM0, COM4, or whatever, depending on the USB input that you're using. And the baud rate, as I mentioned before, is the same one as the serial baud rate of the Arduino. And this line will work perfectly fine as long as you're running the code on your Windows machine, but the code is not, in the end, running on a Windows machine. I just use this line for debugging and developing the code, which I'm doing on my laptop. As soon as you switch to the BTT-Pi, as soon as you upload it there, or like developing on any Linux machine, you need to address the COM port differently. In my case, it's TTY USB 0. It might be USB 1 or USB 2 in your case, but you will figure that out. This sleeping time is also important because the serial communication will need a second to be initialized. So it's just a good idea to put a little bit of a delay in here. Then the next important thing is your Mapbox access token, which is just an API key that you can get from Mapbox, and you will need to insert this here. The app is then what we actually see in the browser. This is what I just showed you. And every time when this app is being updated, this function will run. And in this function, we are reading everything from the Arduino serial communication that we initialized at the beginning, and then try to extract latitude and longitude data from it. This extraction of latitude and longitude data will look for the delimiter that we put between them, and then make two lists and append all latitudes and longitudes that it received to those lists and return them. This if clause is obviously not necessary. You can just delete it. It has just been the result of some debugging stuff. Um, we are having two lists called lat and long, and we are then appending the lists that we just received to them. So lat will be a list of lists and long as well. And then we are adding a trace to the figure that we initialized previously. And this figure is basically like we are plotting the map from Mapbox and then scattering latitude and longitude data onto it. And every time that we add a trace, we are scattering the last lists that we just received from the Arduino. And the rest is just some like design stuff, the size of the markers and color. And here in the layout, we are centering the map at the very last pair of coordinates that we receive. Just one more thing, one more important thing. Um, the Dash app that we just had a look at is running on a server which is hosted by the BTT-Pi. And when we put as a host the local host, and we are connected with our laptop in the same Wi-Fi network, we can then access this server and the Dash app via the browser, just in the same way that I showed it previously. We just need to put the correct IP address and this port in the browser, and we're good to go. And we will see the app on our laptop, even though it's been hosted on the Big Tree Tech Pi. Now, the last thing that's left is having a look at the resulting plots. And as you can see, they're not exactly beautiful. And the main reason for this is that the accuracy of the GNSS sensor is at just 2.5 meters, which is not just a constant offset or so. Actually, the current location is jumping around back and forth, even when the rover is standing still. So that makes for most of the inaccuracy. And that could have easily been minimized if I just drove a much larger letter pi, but I could repeatedly prove that the rover is making exactly those movements that I wanted it to make. And I could repeatedly prove that the GNSS data transmission is working as it was supposed to. And then I just stopped the project, and I thought it deserved to be done at some point because I already put so much time and effort into all of the debugging. So yeah, the life of the pioneer is finally over, and I'm pretty happy and I'm pretty proud of the pioneer, and I'm super happy with this project. And also, don't be shy to just scroll around the project description at Instructables. I have a lot of additional information in here, especially regarding the setup of the Big Tree Tech Pi. I also have a list of the exact sensors that I used. You also have the possibility to donate something if you want to. And yeah, it's been so much fun to do this project, but in a way, I'm also happy it's over. Thank you for watching, and maybe see you another time. Goodbye.